Hello, this is Paul. I'm going to be talking to you about the crystal tester as part of the extra credit of this project. So this crystal tester tests crystals between 1 megahertz and 30 megahertz. Provided the crystals are good, it will turn the LED on. So this can be broken up into several parts. This is going to be the feedback and amplification for the crystal oscillator. This setup is called the Corpitz crystal oscillator. Fair chance I pronounced that wrong. And we'll look at this, and this is more or less a switch. Since we haven't talked about crystals before, I wrote it out this way. It's an easier way to look at it. An inductor, resistor, capacitor, and our load capacitors. So this part here on the left is the crystal, and this would be our load from our circuit. So this CC capacitance is just a parasitic capacitance, very small, and we won't talk about that much again. This resistance is the resistance across this crystal, also small, but it'll certainly come up again. Inductance and capacitance, which is what creates our oscillation, our LC circuit. And this is something what our circuit would look like. Got our frequency, but the amplitude is unstable because there's resistance in the circuit, which is where our emitter follower comes in. So I drew it out so that it didn't have the feedback circuit in it. And we can see here, IB is 25 microamps. IC is 7.58 milliamps. IE is 7.61 milliamps. I don't think this camera is ever going to focus. I worked out this model here. You can see some of that math. So RE is 3.42. Input impedance, output impedance, gain, which is about 1. Current gain, a little bit more important in this circuit, 24. So to calculate the gain in the circuit, there's two parts to it. There's going to be a gain from the feedback, and there's going to be a gain from the transistor. So work out the gain from the feedback. We have our V out and V in, which I've also modeled over here, so you can get an idea of where this is coming from. And from this point on, we're going to be talking about AC. So when you see RE, probably should choose a better one for that. It's not the resistance for the emitter, that's the resistance for the crystal. So a long way to work this out. Kirchhoff's current law. Let's model V out is the current times everything has to cross, which means gain is going to be this here. And the reason why I did it this way is so everything will cancel out later on, in case you're wondering that now. So if it's perfectly tuned, that means the inductance and the capacitance will be equal, and that'll cause a lot of cancellations, which will lead us to this for our gain equation. More intuitive way of looking at it is you can see that this is just a voltage divider, the capacitance voltage divider. When we look at that, you can see that V out equals V in times C2, C1 plus C2. And to get our gain, just solve it for VI over V out, which gets us to the same place in 2 steps. But it's nice to see it worked out the long way, so you know that the intuitive way is actually true. From here on out, I'm working out the gain for the transistor. So the gain is going to be transductance times the load. 1 plus transductance times the load. Transductance is going to be 0.29. Our load, a little more difficult to work out, but it's essentially just parallel and series resistances, or impedances. and most of it cancels out nicely, provided it's a tuned circuit. Otherwise, nothing will cancel out nicely. So, and this works out to this here. And I didn't bother to solve it for this circuit because I don't actually know what RE is. It could be, I know it's small, but I don't know what it is. So when I looked up how to solve for this, I found this equation here. So transductance times our two load capacitors must be greater than RE. For the signal to be stable, we need to have a gain of 1. So as long as it satisfies this, it'll work. And we know that RE is relatively small, so it should be easy to pick capacitors that will be much greater than that. So some other fun facts. I did an account for any parasitic capacitance. That's what I was looking for. There'll be parasitic capacitance across the transistor and across the crystal with high frequency, which we're well into. And also keep in mind that a large C2 will short this out. So you can see here, if C2 is large, it'll have a low impedance, and the AC will just be a short across it. So it won't so much act as a very good voltage divider. So in order to get the appropriate low capacitance, you will likely choose C1 to be larger than C2. For the second half of the circuit, you can see here our VN is from our amplification feedback side. This can feed through these LEDs, charge this capacitor, and flip this transistor on and off. So I believe we'll get a circuit something like this. So this VI is positive, it charges the capacitor. As VI is low and negative, capacitor will discharge, giving us kind of a sawtooth look. And when the transistor is on, it will allow current to pass through, turning this LED on. The LED will be flickering on and off at a relatively high frequency, so we won't be able to see it flicker on and off, but it'll look like a pulse width modulation or bit angle modulation, where the LED is flashing at full brightness on and off, but only for a moment. I didn't do a DC or gain analysis on this transistor, mostly because it doesn't matter. It's really just a switch turning on and off. There is no gain, almost certainly a loss. But we only care if the LED is turning on or off. We don't really care what the gain is or any output on here at all. Just as long as current can pass through it, such that the LED turns on, is good.